will cover a program's memory spaces and allocators to use it as desired. You would already know that an executable code when run gets loaded in the memory as instruction codes. Every object instance created within code need to be stored in memory. ZIG allows you to manage these data objects at three primary different memory spaces: global data register, stack, and heap. ZIG has a concept of compile time known values and runtime known values. ZIG compiler's priority here is to identify the memory size required for variable value of which can be inferred at compile time. A fixed size is known for other variables if they have a fixed size type during compilation. Even if their value is not known, the size to store can be inferred. But say for a string object, which internally is a variable-sized array of constant U8 values, could have 5 characters or 500, so any struct that might have a string member does not have an explicitly fixed size at compile time as well. In the sample code here, both constants name and array have their values inline, thus sizes are measurable at compile time, so compile time known values. In the sample code I'm writing, we have a constant string within the function itself and not passed, thus the size and length both are known at compile time itself. We'll run it quickly to make our first code run lucky simple. A function arguments depend on the value passed, as in the book's sample code input length gets passed a variable-sized array of constant U8 integers. So the size of these would be known at runtime, although we do know the length would be of type usize and thus the return type's inferred size is known at compile time. Global data register is data section in ZIG program that manages values known at compile time. As we have discussed, these involve constants and other literal values directly mentioned all over the program logic. Programmers don't deliberately manage it, it simply exists and gets referred to by your instruction codes. Stack and heap are something which you need to care for if performance of your program needs improvement and/or you're dealing with interesting data objects. Your program would generally use a combination of both. Stack is primarily used for values with fixed length, heap for objects that may grow in memory space with time, so from what we mentioned earlier, stack for compile time known values and heap for runtime known stuff. Accessing stack memory works faster than heap, but the size of stack is limited as well. It's giving a bit more details for green coders. Stack memory uses last in first out data structure mechanism for adding and retrieving deleting value onto it. Every function call reserves a compile time known memory on stack for that call. It contains arguments and local objects. For example, when add function gets called, this reserves a space upon stack for size required for arguments x and y for local constant result, and constant r object declared in outer scope. The first stack space here reserved would be for the main function. Stack memory frees itself at the end of function scope. The same logic applies to other scopes defined by curly braces, as a local variable declared within an if-else block will go away at the end of it. As in the example here, constant index is only available every iteration of loop. Heap memory is for objects that need flexible lifecycle to sustain beyond a function's scope. It's also suitable for objects with dynamic sizing. So for writing servers where size of incoming requests is dynamic or data clients where matched entries are query-based, heap seems a better fit. The program logic explicitly manages allocation and deallocation of heap memory space. Majority ZIG allocators manage heap memory space, with exceptions. Most common allocator is page allocator that uses heap. Then there's also fixed buffer allocator that allocates memory in a fixed buffer on stack, not heap, so works for comp time size known objects. Arena allocator also behaves a bit special where it takes in a child allocator to allocate multiple times and free memory at once using deinit. As a summary, if you didn't create an object using allocate or create method of an allocator, it's probably on stack. Stack is limited in size. If you've ever faced or heard of stack overflow error, that is when the overall stack memory space allocated to a running program falls short to the creation retrieval of a memory address. So an infinite recursion often results in it. As in the example here, allocating a far larger array than can fit on stack would cause a segmentation fault due to stack overflow. Let's write a function cause stack overflow with the copied code from sample to have a live test. We'll call it from main and run to test. Let's comment the call for Stack Overflow error. ZIG standard library does no hidden memory allocations. If any call from standard library need to use an allocator, need to be passed by user. For example, function allocprint that creates new string using format specifiers similar to common sprintf C function needs an allocator to be passed to store the output. Below we see an example code block that instantiates a general purpose allocator and passes it to std format allocprint along with string filler and arguments to interpolate. Let's write a similar piece in our ZIG example to run and test. So we'll create GPA, a heap allocator. Pass it to allocprint along with a hello message. We'll modify our s constant and pass it Jack as name. Then print the formatted message. ZIG offers multiple allocators through std heap module. Every allocator object is built atop allocator interface in ZIG that must have functions alloc, create, free, and destroy, so they are replaceable. Object in functions that have growing size or have an unknown length boundaries require the use of allocators, and in case when function need to return pointer to a local object can only sustain function scope if in heap. Let's add a new function to explore this idea further, adding a new function bar with 2 arguments and return type of pointer to a U8 number. Running this causes no error. ZIG automatically handles keeping the variable address space available across these function calls. Page allocator is a basic allocator that simply asks OS2 for entire pages of memory. Could turn out inefficient for small chunks. If linking libc, likely choice is C allocator, at least for main allocator. If need to use same allocator in multiple threads, use the choice wrapped around thread safe allocator. To manage tests for out-of-memory error, using std testing failing allocator shall work well. For a simple test, std testing allocator. If no specific cases apply, general purpose allocator would be a sane choice. We have already covered fixed buffer allocator and arena allocator, which are not heap dependent. Let us add general purpose allocator to our newly created bar function to be used for allocation and returned as a pointer. Actually, let us just move this GPA usage into the main block itself. Let me tweak the value for GPA sample. Also, if we remove asterisk dereferencing, it will rather be the address value to it. Let's have both printed and rerun to showcase a proper output. If we were using C allocator, which is alias to C languages malloc, we need ZIG compile time flag -lc. Full page sizes allocated via page allocator is commonly 4 KB in heap since the 1960s. Different allocated pages mapping is arbitrary and not contiguous. On a separate note, If larger page sizes are suited to your data context, using super pages or huge pages would help TLB, that is translation look-aside buffer, to have optimal page references. With fixed buffer allocator and thread-safe fixed buffer allocator, a fixed-sized buffer gets reserved in code and used as input for the allocator. Thus these can store memory in stack or heap. In the sample code, a stack-based fixed buffer allocator is being used to create a 10-element sized allocator. Heap-based fixed buffer allocator would be used when the size limit is maintained, but the size itself is large enough to pick heap. As in the second sample code for the section, a heap.alloc gets used to allocate 100 MB of memory. Arena allocator is a specialized allocator where you require several allocations but suited to free all at once. It is initialized with a child allocator that gets used to allocate, then doing dinit freeze it all. Cases like video games frame renders, web servers request processing, parsers with cyclical short-lived states. In the sample code, general purpose allocator gets passed to initialize arena allocator, which then allocates 3 times, and finally a single dinit of arena allocator frees all. Alloc method takes in 2 inputs, the type of value it stores and max count of values it can store. As an example here, it allocates space for 50 U8 values. We defer free method call on allocator to explicitly free the allocated memory. Using stdin to get user input with read until delimiter or EOF method, passing it allocator and delimiter of line change. Let's do a quick run for this sample in our sample code file. We'll have a variable yourname with allocator create for 50 units of U8 values and defer the free call for it. For loop for range to your name length and assign 0 to all. Then create a nameReader constant with stdinReader and calling the read method on it with allocator passed to store the input at. Then let's print the input as string. Oh, let's fix create with alloc method name and run. It waits for input here. Let's add a prompt for input so it's not ambiguous. Alloc and free to allocate multiple elements at once. Create and destroy method get used to allocate and free single item. In the example code here, a single item of user object gets created with create and free with destroy. This is it for this session.